Dex is a domain-specific language designed for configuring security policies used by the Shape security division of F5 networks. Domain-specific, the domain here is protecting companies, sites, mobile apps, whatever, from bot attacks. So the reality is that most people are probably unaware of is that if you have a major consumer-facing website, then the majority of the traffic it's getting is not real traffic, but actually hostile attacks by automation, by bots. Whether it's the obvious financial stuff, but anything of value that's consumer-facing, any kind of point system, credits, frequent flyer miles, gift cards, you name it. That's generally known as credential stuffing. There's also scraping of websites to gather information about the price structure of consumer sites and so forth so they can be undercut. There's all kinds of things like that. And this is the majority of incoming traffic for a lot of sites. So you have to defend against this, and the defenses have to be customized per site to some degree. I mean, there's a lot of general purpose stuff that's probably true for most sites, but the exact configuration varies with the site. Which bots are legitimate, because there's also positive, good automation, not just bad automation. Which are the entry points, which pages are more important to protect, etc., etc. So Dex is an external DSL, which Shape developed, I think around 2016, before I got there. And this is the domain it works on. And you've probably used Dex unknowingly, because if you live in the United States, certainly, and you've not lived under a rock for the past few years and actually access major websites, airlines, banks, hotel chains, you name it, major sites like that, then they very likely are using Dex in the sense that you've done some session or transaction with that site, and that has provoked a Dex program to run and evaluate that to see if you're a legitimate customer or if you're a bot. So Dex is a purely functional language, and it's not Turing-complete for the obvious reason. As a configuration language, we really don't want our configurations to go into an infinite loop. It's statically typed. And we'll see a little more detail. Let's start with non-Turing complete. This is enforced because there's no recursion in the language, no looping constructs. The only way you can repeat something, you can iterate over something, is via list comprehensions. And so as long as your lists are finite, your programs do not diverge. Purely functional. There are some of the classic issues around that, around I/O and the foreign function interface. So we don't do anything very fancy. There are no monads, streams, effect systems, nothing that you'd see in a full-blown academic functional language. Things are a lot simpler. Essentially, we view the inputs as parameters to the program. So a Dex program, when it runs, it gets a set of inputs, and it runs on those, and they're not going to change, so we can keep things referentially transparent. Syntactically, they don't look like parameters. They're these data declarations where you declare a variable and give its type, and the sort of extra-linguistic mechanism that drives execution will see to the binding of that variable, just like passing in a parameter. Outputs, that's less difficult, right? There's no result we're really interested in, but there is a analogous top-level declaration. There's a report construct. You name a variable, and it reports the value of that variable to the output. There also is a thing called a flag, which is used for anomaly detection. So it's a Boolean value, you declare it, and you say you make it dependent on a Boolean expression, and if that Boolean expression is true, then the flag is raised, as it were, and it will be reported to the output. The FFI is also always a challenge. Generally, whatever semantic guarantees your language have, they go out the window when you have an FFI, because the FFI is likely to undermine it and you have no control. So you have to be very careful about that. What these things look like in our case, they look like sort of fairly standard extern declarations, external functions. These are Java functions because the system runs on the JVM. Basically all bets are off. There are no guarantees. You're responsible. The system assumes that these are pure functions and that they always terminate. Obviously, the termination guarantees of the language don't hold if you call a function that doesn't terminate, and we can't control what a Java function does. As far as pure functional, yes, it has to return the same results for the same inputs. If it does not, well, we'll get different results and things may go bad, but it depends. We basically are free to cache the results for a given input or not. We're free to call it once or many times at any order at any point in execution. If it's a pure function, none of this will make any difference, but if it isn't, then yeah, you'll get rubbish and garbage in, garbage out. It's what you deserve. Fortunately, most users don't have to deal with this. The Java FFI is largely wrapped up in a standard library where people who are more careful and understand this properly have made all these connections, and so it's not been an actual problem in practice. Now, there's a type system. At its root, it's sort of a Hindley-Milner style thing. It mostly works, but it has had many of the problems that are typically associated with Hindley-Milner. The error messages can be very hard to understand. Small changes to the program can have a very large impact. We have cases where adding code to a type-safe program, not changing the existing code, but adding other code that is also actually type-safe, cause the inference overall to fail, and that can be very disturbing to users. And for those reasons, we're transitioning to a local type inference approach instead. But we found a way to make that compatible with what we had before, and so that's just one of the lessons learned, or well known actually, but learned again here. Another great lesson to be learned is around nulls. So it is in the nature of the domain that inputs may often be undefined. They may be derived from web page headers or all kinds of network information, and some of this information may be provided or not depending on all kinds of circumstances, so it may often not be there, and that results in having an input of null. Now, in such a situation, we don't actually want to necessarily crash when someone accesses a null, because just as diverging in a configuration is rather bad, crashing is also rather bad. So instead, the semantics are a little strange. It tends to propagate nulls. So you call a function with a null argument, it returns null, and it keeps going until you test it, and then produce an alternate value, a default of some sort, etc. Now, in practice, this is easy to miss by programmers and is a fairly significant problem. It isn't, things don't crash, but people get suboptimal results, unexpected results when something is null. And so we want to fix that, so we're introducing non-nullable types to the system, which it didn't have before, so that we can statically enforce the discipline where people actually catch these things. Here's a complete Dex program. And as you can see, the outputs and the inputs are top-level declarations. It's a module M. It has an input x, which is an integer. It's going to echo that input to the output with the report at the bottom there. And if x is greater than 100, which is this variable threshold, then it's also going to report threshold exceeded to the output. Generally, the whole execution of the program is driven by the outputs, sort of lazily. If there's an output that therefore requires some computation to be done to compute it, that will cause that computation to be done. Otherwise, it won't happen. So for example, here we have this let don't care, which no one is referencing, and we won't compute it. But if it is references by the outputs, right, then it will get computed, and only what's driven by the outputs will be computed. Now, this isn't really lazy evaluation in the classical sense, because we still evaluate function arguments in applicative order. So all arguments to a function are evaluated. So if someone references a function, then all the pieces that are passed into it are going to be evaluated, and so on down in the function body and so forth. The output, however, can be computed in any order. It's not specified, as long as, of course, dependencies are respected. And as long as it's pure functional, it doesn't matter. But as I said, if anything like in the FFI doesn't respect that, then you'll get strange results. Then there's the issue of modularity. In DSLs, external DSLs, you tend to find that even though you try to initially keep them very simple, all the problems that full-fledged programming languages have will eventually come back and bite you, and you'll have to deal with them. So there's a standard kind of typical module construct that we saw in the previous slide, where a module includes all these things, and it has a conventional import mechanism between modules and sort of the boring stuff you'd expect. Though again, all of this has to be specified and implemented again over and over. But in addition, there's a notion of a component, or originally they called it a feature. And it's sort of a mix-in module kind of mechanism. And it does the same thing that inheritance and mix-ins and stuff do in standard languages. It basically is a way to reuse existing definitions with overrides of selected elements that need to be just a bit different. So that's a very handy thing in programming in general, and it has turned out to be pretty essential here as well. It's a little strange in its semantics, but it's sort of the people who did this independently, and I'm sure unawares, reinvented mechanisms that are closely related to my own research from 30 years ago, and to the Scala cake pattern, for example, for people who are familiar with that, where you basically have these complete definitions that are their self-references merged so that you get a compound module out of a number of component modules. And the other strange thing is that most of this component mechanism was really implemented in an interactive kind of IDE-like tool, not with real linguistic constructs. So it does its job, but people aren't really aware of that. So again, part of my job is to put all this on a firm linguistic basis, and we're doing that. So that's the essence of it. The lessons here are that doing your own dedicated external DSL for configuration can be a huge win, as it has for Shape, because it really fulfills a business critical function, and it does it much better than the typical hacks that you see in industry, whatever it is, XML, JSON, YAML, blah, blah, blah. On the other hand, as with many other DSLs, most of the problems you see in a general purpose language eventually arise and have to be dealt with. Types, inheritance, modularity, foreign functions, questions of what to do if it's functional or not, and how to deal with the problems that functional languages have dealing with the outside world and with state and things like that. The other lesson is that Turing completeness is overrated. Dex, in fact, my experience with Dex convinced me to start working on ShapeRank, which is a non-Turing complete general purpose language, again, where the shape of the data dictates how things are computed. And I'm talking about that at a different workshop here at Splash, at Rebels. And so that's an important lesson. I think there's lots of potential there for computing without insisting on some of the mechanisms that let you have infinite loops and so forth. So I'd like to thank you for listening, and to thank all the people who were involved in the original design and implementation of Dex, because I'm a newcomer to that project, and most of the work has been done before. I'm just kind of trying to bring a more programming language centric expertise to it to clean it up. The fact that it can be cleaned up is, in my experience in industry, pretty remarkable. So that's all I had. Thank you, and if you have any questions, feel free to ask.